Gracias a todos por estar acá y lo que les cuento es que a partir de ahora voy a cambiar a inglés. Our guest, Connor, just arrived yesterday. He understands a little bit of Spanish because he has some familiarity with Italian. So maybe if you would like to, doesn't feel that comfortable asking questions in English, want to try Spanish, I think we could figure out, and he has been really nice. Also, he will try to accommodate, no, in speed or whatsoever. So the idea of this workshop is to introduce one topic that actually we choose in terms of the amount of techniques that it can offer you as young students, young researchers, no, starting your work. And one of them is, we thought that Monge-Ampère equations are ideal for that because of connections with well, many different topics like optimal transport and also differential geometry. Okay. After having said that, so this first lecture is going to be a warm-up. These are some prerequisites, preliminaries that I would like to discuss so we are all on board. Also, we give Connor the opportunity to see how it could be the interaction. Please, the most important thing is that you come here and ask questions. All questions are valid. We will take the pace that you give us, no? Also in the program, you're going to see, well, starting tomorrow and Wednesday, there is a morning session of lectures by Connor, and in the afternoon we have some problem sessions. And they are very important. There are going to be some homework, and it will give us the opportunity to interact with Connor. Also on Thursday, there is a office hours kind of session where I think you will have the opportunity also to discuss all kinds of topics. No? What I think is going to happen is that the lectures are going to start from very basic classic material, and then eventually there is going to be an overview of what are the future directions, where is the field going, where could be some interesting problems. So please, I think the most important thing is that you are not shy and you ask questions and we get to know everybody. Okay? So I think there are many people here. I know some faces already, some names. I'm not going to ask the names, but I will try to talk with as many people as possible on the breaks and during the lunch. So let me start now. What I want to discuss now is some preliminary material on convex analysis, and towards the end we are also going to discuss some classic results in elliptic PDEs. Okay? I don't assume that you know this. This is not necessarily material that you see. Well, some of them is material from the real analysis, but some other material not necessarily. So ask questions. For sure, the PDE part is also a higher level. Okay. So let me start with a very basic concept, a convex set. A convex set is a set where every segment is completely contained in the set. Okay? Some examples. A half space is a convex set. No? So you take all the numbers such that xn is positive. To give an example, any intersection of convex sets is a convex set. Why? Anybody? Please, I tell you, don't be shy. Yeah, you think it's easy, no? Exactly, no? So the property that you have to check is that if you have two endpoints, the whole segment is contained on the set, no? So if it's in the intersection of two half spaces, no, both of those points are in both of half spaces. Therefore, if the segment is in both of half spaces, so is in the intersection. So that actually shows us the same argument is that the third one. Any intersection of convex sets is a convex set. It's the same proof, no? More interesting is that also you can recover any convex set as the intersection of a family of half spaces. Okay? And we are going to see in a moment which half spaces you may need to take. No? These are the supporting half spaces. Another way to construct convex sets is give me an arbitrary subset of Rn and look at all the convex combinations. So this for any 2 points in A and any parameter between 0 and 1, look at the linear combination with these coefficients. Or in other words, look at all the points in the segment with endpoints x and y. Yeah? And all those points again give you a convex set. So supporting plane is a plane that divides the Euclidean space into pieces such that one of them contains, well, the closure of one of them contains the convex set and the other doesn't. Okay? Moreover, you also need to have that in the hyperplane that the boundary of this hyperspace contains one of the points. Okay? At least if the convex set is closed, no? And these give us two types of situations that can arise, no, with these supporting planes. In one of them, we say that the point is exposed if the intersection of this hyperplane with the convex set of the closure of the convex set is just that point, no? Is that there is a unique intersection. Otherwise, it's called unexposed. We say that the convex set is strictly convex if every boundary point is exposed. Okay? So this cannot happen. You cannot have flat regions. Okay?
So let's see, just in that last picture,
Mm-hmm.
on the corners of the domain, do you consider those points exposed or unexposed?
Is that for me or is that a question for?
For you.
For me, I would say that these are exposed, no? Because you can draw up a plane here, no, that but just contain the vertex, no, of that in that picture. Good. Now here is a result, no? Every compact convex set is the closure of the convex hull, no, of its exposed points. So, for example, here, if we take all these points on the boundary, yeah, we are not going to count this straight segment and look at the convex hull, and then look at the closure. What we obtain is what we recover is the original convex set. It's fairly intuitive. I'm not going to give a proof, and not necessarily easy the proof. Okay, but is this condition of being compact actually necessary? Well, it has to be close, no? Because at the end we are taking the closure of the convex hull, so that's not probably the relevant issue here. But do we really need the set to be bounded for this statement to be true? Can you give me an example of a convex set that is not the closure of the convex hull of its exposed points? So what is the easiest convex set that we can think of that is not bounded? A half space, yeah? What are the exposed points of the half space? Are those exposed? There are no exposed points for the half space. So that's a counterexample, no? Because what are you going to generate? What are you going to span with the convex hull of an empty set is going to be empty, no? Or, for example, you can also have a convex cone, no? A cone where that is generated by a convex set, no? And then you see that every point on the boundary is going to be unexposed, no? Because it actually contains the whole ray, no? That goes from the point to the vertex. Up?
Except for the vertex.
Except for the vertex, yeah? And the vertex is not going to generate. But there is sort of a reciprocal. And if you have a closed set without exposed points, then it necessarily contains a line. Okay? So kind of the convex cone is not an example because the vertex is exposed, no? But clearly, if you have any convex set and then do sort of a cylinder, that's an example of this theorem. Okay, another important result here in convex geometry is the following. Well, I'm going to read the lemma and then I'm going to say more or less what is the philosophical intuition about this. So you have C is open and bounded convex set, then there exists a unique ellipsoid that is contained in C, has maximal volume, and it satisfies that n times, if you do a dilation where n is the dimension, then this one contains the convex set. So what this says is, well, remember that ellipsoids are modulo affine transformation balls, no? So if you dilate, no, in some appropriate system of coordinates, you can transform this into a ball. So essentially what this is saying is that the convex set is modulo an affine transformation comparable with the unit ball. Okay? Well, let's see the idea of the proof. I will say that it's fairly straightforward to say that there exists an ellipsoid of maximal volume. Yeah, this is an argument by compactness, no? There is you take a sequence of ellipsoid that maximize the volume, yeah? This sequence is compact, no? Because it's determined by a finite number of parameters, yeah? The coefficients of the matrix and the center of the ellipsoid. So they have an accumulation point. The fact that it's unique, well, that has to do with the convexity of the determinant to the power 1 over n, no? Or the convexity of the determinant. Sure.
N is the dimension of Rn?
Yes. Yes. And actually, I think this also this estimate is sharp, no? The example I think is a triangle of a tetrahedron, something like that, no?
Exactly.
The
simplex with n plus 1.
Exactly. So what I'm going to focus is not on the existence and uniqueness of the maximal ellipsoid. What I'm going to focus is once you have the maximal ellipsoid, see that the dilation contains C. So first of all, remember modulo an affine change of coordinates. I'm going to assume that the ellipsoid is a unit ball. Yeah, I translate the center to the origin of my coordinate system and then dilate the axis such that all of them are equal to 1. And the goal is to show that the ball of radius n contains C. Well, let's see what happens by contradiction. No? Let's take a point of distance rho to the origin, and without loss of generality, I'm going to say rho times e to e sub n, where rho is a number larger than n. And let me assume that it belongs to the convex set C. But what happens? The unit ball belongs to the convex set. This point belongs to the convex set. And remember that all the segments that you can form with this point and any other point here also is going to belong to the set. So kind of this cone with this, I don't know, ice cream cone belongs to the convex set. Okay? And now we are going to see that because of this configuration, we have enough space to find another ellipsoid with a larger volume. So what's the idea? I'm going to flow the unit ball with a vector field that does two things. First of all, I'm going to keep the unit ball inside of my ice cream cone, yeah? And at the same time, I want to increase the volume. So I figured out an ODE system like this. I'm going to take my vector field such that the first component of the velocity is x1 plus 1. So you see, for example, here at this point in the ball, which is x1 equals minus 1, this coordinate is equal to 0, so this one is not moving. And the second one is going to be minus lambda x prime, no? The following x2, x3, xn coordinates. So this is more or less like how the vector field is going to look, no? So it's going to point inwards to this cone, and if you choose lambda such that is between these two numbers, and this is always possible because by hypothesis rho was larger than n. So what you get is a flow, and this is a computation. I'm not saying that is straightforward, but if you do it, you will see that, first of all, the vector field always points inward, so the unit ball is going to flow into something inside of the cone, at least for a short amount of time, and also it's going to increase the volume. How do you compute the volume? How the volume is changing in a linear system of ODEs? That's a question. You remember there was a tool in ODEs called Liouville's theorem. And what is the operator behind Liouville's theorem to compute the volume? Jacobian. The Jacobian, and then you need to take what else? Has to the Jacobian give you how the volume changed from one time to other, no? You need to take the determinant of the Jacobian, no? And when you take the derivative of that, which operator is playing a role there? The divergence of V. So in order to see that this is increasing the volume, what you need to compute is the divergence of this quantity, no? And see that it's going to be bigger than 1. Okay. So a few consequences of John's lemma, or actually the idea behind the proof, okay? So we have an open-bounded convex set, and well, in the first item we have that it contains the unit ball, or it actually can be replaced with any ball of radius r, and then by scaling you could get a similar conclusion, and the conclusion is that C, then it has to be contained in a ball of radius capital R, where capital R depends on the volume of C. Okay? So by having some space inside, I know that C has to be bounded, no? I can control the outside coming from a hypothesis from the inside. So this reminds us what is going on with John's lemma. The second one tells us, well, the other direction, no? If C is contained in the unit ball, then there exists a radius r depending on the volume such that there exists some ball of radius r containing C. Okay, so here we are controlling the interior in terms of a bound on the outside. So the idea for the first one, so we have already that B1 is containing C, and we would like to show that C is containing BR. So this is, well, essentially the same picture as before. If X is an arbitrary point in Z, I would like to show that X is not going to be too large, no? At least the modulus of X is not going to be too large. So if X is in C and B1 is in C, no? Also all the segments that connect X with the unit balls are in Z. So this kind of, again, ice cream cone is contained in C, but you can compute, for example, the volume of this figure, and that volume is comparable with how large X is, no? The area of a triangle is base times height. Base is order 1, and height is order x, no? So therefore, I should say K is this ice cream cone. So the volume of K is comparable with Cx, but we already know that K is contained in C, so C bounds the norm of X. So X cannot be too large. The other direction, the other part is, now let us assume that C is contained in the ball of radius 1, and we would like to show that there is a ball of some fixed radius containing in C. So let's take E to be the ellipsoid of maximal volume, yeah? So now we know that C is contained in n times this dilation of the ellipsoid E, but then we get to bound the smallest semi-axis of this ellipsoid from below. And the situation is that because this volume is known, let's say this is this number over here, and then this one, the volume of this dilation have to be larger or equal than this one, no? So what we're going to do is to take X as the center of the ellipsoid, yeah? And to take then small r as the smallest semi-axis. Have a problem here, I'm not seeing when I'm using that, when I'm using that B1 contains C. Well, I'm using that B1 contains C in order to get a bound on the volume of the ellipsoid, I think, if I'm not getting. Okay. So any questions? Next thing I would like to comment is a projection lemma, no? So if we define for any convex set the projection, meaning that I'm going to take the closest point in the convex set to a given point x, then this function is one Lipsius, meaning that the distances between the projections are going to be smaller or equal than the distance between the original points. It's also fairly intuitive, and the proof is not that hard, no? So it's again, think about the supporting planes. So for every point x, when I look at the projection, there is a supporting plane to the convex set at this, well, assuming that x is not in C, otherwise the result is trivial, it's easier, no? So the interesting result is where x and y are outside of the convex set, no? So in that case, we can take at the projections the supporting planes. So the fact that there exists a supporting plane, what it's telling me is that these two vectors points in opposite directions, yeah, with respect to the supporting plane. So x minus pi points in this direction, and pi y minus pi x, because pi y belongs to the closure of the convex set, it points, but at least either is orthogonal or it points in the opposite direction. So this inner product has to be smaller or equal than 0. And the third argument you can do also by interchanging x and y, yeah? And then if you add them up, what you get is this inequality, no? And from here it's clear that Cauchy-Schwarz, and then cancel this factor, you get the desired inequality. What is one of the consequences of this projection lemma is that whenever you get C contained, for example, in a ball of radius r, yeah, then the perimeter of the ball of radius r controls the perimeter of the convex set. And the same result is also going to be true if we replace the ball for any convex set. And here the idea is that you have to remember what is the definition of the Hausdorff measure, no? You have to do a covering with sets of diameter less than delta, yeah? Take the best possible covering such that you are minimizing the sum of the diameters to the power n minus 1, and then take delta to 0. Okay? And a fact is that, for example, if you have a Lipsius function, then you have this sort of inequalities. Okay? In this case, because we have that this is a contraction, then the Lipsius, the constant here is going to be 1. Okay, so we were talking about Lipsius function. Actually, let me give also a quick review what this means. So a function is called Lipsius if when you take this different quotient, it's always bounded by a constant. Okay? And that constant we call the semi-norm of the function. Okay? It may be the case that the function is not Lipsius in the whole domain, but it's Lipsius for every compact set contained in that domain. For example, x squared. X squared is a function in Rn, no? That is going to be Lipsius in every bounded set, yeah? But it's not necessarily Lipsius in the whole of Rn. Geometrically, what is going on is that the graph of U is bounded from above and below by these cones. These are cones with vertex in the point x, comma u of x, and then you have an opening of size L, no? Or meaning that L is the slope of this rays on the cone. Okay? So a few properties. For example, the norm of the point x is always Lipsius. Why is this true? How can you, what have you need to see in order to check that this is Lipsius and actually the Lipsius constant is equal to 1? What is the inequality behind this example? Exactly, the triangle inequality. Another example, if you take any function that is differentiable and the gradient is bounded, then the function is Lipsius. Why? The mean value theorem, exactly. And moreover, well,
some regularity on the domain, right?
We need some regularity. Okay, let me say that the domain is convex. Okay, because I think what Connor is thinking, it may happen, is that if you have something like this, no? The ball minus a segment, yeah? You may have that the function is u equals to the, in 2 dimensions, argument of theta, yeah? And it's going to be Lipsius. Well, it's differentiable, the derivative is bounded, but if you compare 2 points here, yeah, where the segment crosses, where you have the discontinuity, you're going to fail the Lipsius criteria, no? So that's the that's the problem. Thank you if I missed that. Another example is, in particular, no, if your function is of class C1, yeah, then it immediately is locally Lipsius, okay? And here I don't have that problem, no, because of what it means to be a compact subset within the relative topology of omega. And more interesting is that almost all the examples are something like this. So if U is locally Lipsius, then it's differentiable outside of a set of measure 0. So at almost every point, you can compute the derivative. And that derivative is going to be bounded, no? At least on the compact sets. Another way to visualize Lipsius function that sometimes is very useful is, well, remember in the previous picture we're saying that U is controlled. At every point you can put these cones from above and from below. But actually it's enough to say that you can put the cones from above. Any way to see why this is true? So let's say I have a function that only satisfies, you can always put the cones from above with opening L. So that means algebraically that what you're satisfying is this inequality. Yeah? So this means ux or uy minus ux is smaller or equal than ly minus x. In my definition, I need the absolute value of uy minus ux. But now I have it without that absolute value. So why? How do I get the other inequality? So let's see if we understand. Can you see on that side? If I write here? So Lipsius means ux minus uy is smaller or equal than lx minus y for every x and y. I'm saying that this condition for every x, y. I'm saying that that is equivalent to say that ux minus uy is smaller or equal than lx minus y. Without the absolute value. So what happens here if you interchange x and y? You get the other inequality. Geometrically, a way to see this also is that if this doesn't hold, no, if you have a point where the cone from below crosses the graph, so you take any point below in this graph, yeah, and look at the cone from above, yeah. But because of the symmetry of the cones, this cone above is going to contain this vertex, yeah. So that contradicts that picture. Make sense? Another way to think about Lipsius function is to say the following. You take the graph and you translate vertically by an amount L times h, and then horizontally by amount h, and then you get a graph that is above your original graph. Okay? So what I'm saying is that you have this inequality for any direction and any positive distance. Okay? And again, the idea is that if you can do this, you can always put the cones from above. Okay? Finally, well, I'm going to comment quickly on this because I think you're not going to use this actually, no, these envelopes. No? Let me just comment because it's also a fun exercise, no? So a function is Lipsius if, well, let me define this lower envelope. I'm going to take at every point a cone of opening 1 over epsilon. So if epsilon is small, this is a very narrow cone, yeah? And I'm going to bring this cone from minus infinity up until it touches the graph of u, yeah? And where it touches, I see where the vertex has a stop. And I do this for every cone, for every possible position of the cone, and what I get is a function u sub epsilon. And if you want to be precise, this is written in the following way. U sub epsilon at x is the supremum between this function, which is a cone with center of x and opening 1 over epsilon, and the graph of u. Okay? And the fact is that this function is Lipsius. Its Lipsius constant is bounded from above by 1 over epsilon, yeah? And is actually the largest Lipsius function that is smaller or equal than u with this Lipsius constant. Okay? So this is a way to approximate an arbitrary function by Lipschitz functions. Okay? So what you see is that as epsilon becomes smaller and smaller, this envelope becomes closer and closer to u. Yeah? but it's not going to converge uniformly, no? Because we don't know a priori that U is Lipsius. If it converges uniformly, we will have that U is Lipsius, okay? I'm sorry, forget about the last part when I said that if a converge uniformly, it will be Lipsius. It's going to converge uniformly, but not necessarily the limit is going to be Lipsius. And finally, a criterion for C1 alpha regularity. What does it mean a function to be C1 alpha regular or CK alpha regular? What it means is that the first 1, 2, 3, 4, 5 k derivatives are bounded, and the kth derivative is Holder continuous with exponent alpha. Okay? Holder continuous is similar to the Lipschitz regularity, and the difference is that here in x minus y to the power 1, you put x minus y to the power alpha. Geometrically, what you're saying is that for example, if we say that a function u is Holder continuous with some alpha between 0 and 1, what it means is that for every point, I can put this cusp, no? That are like the function, this is ux plus constant y minus x to the power alpha. Yeah? I can put this from above and also from below, no? Ux minus c. And to say that C1 alpha is that you can do this both for the first derivatives of u. Okay? So something that is also fairly intuitive is that if u is differentiable, no? So the gradient exists, and you can always say that the oscillation of u from the tangent plane to the graph decays like the distance to the power 1 plus alpha, yeah? Then what you can conclude is that the gradients are Holder continuous and with the exponent alpha. Okay? So let's see quickly what some of the ideas behind this theorem. What I'm actually going to prove is that the gradient is Holder continuous at the origin. And then the same argument you can repeat for every other point, and then you are done. No? And let me assume without loss of generality that at the origin, u is equal to 0 and the gradient is equal to 0. Yeah? So what I want to show is that any other gradient, no, dux for x close to 0, so let's say x in the ball of radius 1, 4, is bounded by some constant times x to the power alpha. Yeah? And I'm going to say that that constant is 10. Okay? We are going to see in the proof what I'm going to choose 10. But for the moment, let me assume that that is not true. Let me proceed by contradiction. No? So there is a point in the ball of radius 1, 4 where the gradient is larger than 10 times x to the power alpha. So this point here. And the point where I'm going to lose the contradiction is not actually x, but it's going to be x followed by the gradient of u, the same distance. No? So the important here in this picture is that from here to here is norm of x, and from here to here is also norm of x, but the direction is given by the gradient of u. And let's see what happens. So what we consider is mu equals to this quotient, and y defined as x plus the gradient times mu, no? So that means that this vector has norm x, no? And what happens? What is the distance between 0 and y? Well, the distance between 0 and y is smaller or equal than by the triangle inequality, 2 times the distance from 0 to x. So it has to be, because x is in the ball of radius 1, 4, y is in the ball of radius 1/2. Yeah? But you see, so 2x larger than y means that 4x to the power 1 plus alpha is larger than y to the power 1 plus alpha. Yeah? Alpha is smaller than 1. On the other hand, if we use the hypothesis, no, that u separates from the linearization with the rate of distance to the power 1 plus alpha, no, we get that this quantity controls u at y. Yeah? So here we are using the hypothesis from 0 to y. Yeah? And now I'm going to use the hypothesis from y to x, from x to y, no? So this quantity, u of y, is bigger or equal than u minus the linearization, no? Which I know, because I know in which direction I'm departing, no? So I get u of x plus, maybe I should write this part. So I get u of x. The hypothesis tells me uy is bigger or equal than ux plus d ux dot y minus x. No? But this part here is mu du at x. So when I do this dot product, what I get is exactly this. And then there is, I forgot, minus distance, which is x to the power 1 plus alpha, no? So I get exactly this quantity. So I know by my hypothesis that this quantity is bigger or equal than 10 times x to the power alpha, and u of x is also bigger or equal than minus x to the power 1 plus alpha. See? So if you add the terms, you get 8x to the power 1 plus alpha, but that's certainly bigger than 4x. Okay? So it's a way to, if you try to visualize it, you need to see that what does it mean to control in terms of these sort of paraboloids, no? From one point to the other, and then use the triangle inequality to get the contradiction. Okay, so let me move to convex functions. So a convex function is one where the average, no, of u at two endpoints of a segment is always bigger or equal than u at the average of the points. Okay? Other way to say it is that the epigraph, so the set that is above the graph of u, is a convex set. And this, usually when I said that u is defined on a set omega and is convex, it could also mean that if omega is not convex, it means that the function u can be extended to a convex function in the whole of Earth. Okay? And we are going to admit the possibility that it takes also the value plus infinity. Okay? For example, if you take a function that is equal to 0 on a convex set and is infinity outside of it, that's a possible convex function. So any affine function is convex. Yeah? You are only looking at the half spaces, no? So the function norm is convex. Again, what is the inequality behind this? The triangle inequality, no? Any function with two derivatives such that the Hessian is a non-negative matrix is also convex. No? This is a fact from calculus. Moreover, there is sort of a reciprocal. If you have a convex function, well, we know that it's not necessarily second order differentiable at every point. We have here the example of the norm. However, it's second order differentiable outside of a set of measure 0. Okay, so almost every point, this is an analogous of the Rademacher theorem for Lipsius function. Convex combinations of convex functions are convex. For example, if you add two convex functions, well, that's not a convex combination, but multiply by 2, no? But if you take the average, yeah, of two convex functions, that's again a convex function. If you take any convex function and multiply by a positive number, that's again a convex function. And that allows me to, the generalization to this is to say that the mollification, so you see the mollification is to do an average of u against a weight that is, well, non-negative and integrates to 1, no? So these mollifications are also convex. And what is the advantage of these functions in PDEs or in many cases? Why we look sometimes at these mollifications? Sorry? Yeah, this is okay. This is also a convolution. Well, what is a very nice property of the convolution that we can take advantage? No, how does this improves the function u? Yeah, if the function eta is smooth, then the convolution is also going to be smooth. And actually, you can also take these weights to be an approximation of the identity, so they become closer and closer to the delta distribution, such that these convolutions get closer and closer uniformly to the function u. Okay, so that's something to keep in mind. I'm not sure if you will use something like this arguments. Maybe. Okay. So some other examples of property to get familiar. If I have a convex function, these level sets, or actually sub-level sets, are convex. I can also replace here 0 by any real number, and it's still true. But it's maybe easier to visualize with 0. Why is this true? So we know that the function is convex if the epigraph is convex. Yeah? And we also know that the intersection of two convex sets is convex. Yeah? So how can you get this as an intersection? So it's the epigraph and the 0 level set. Yeah? There is also a maximum principle. Maybe you are familiar to hear about maximum principles in elliptic PDEs and also in complex analysis. And what is the maximum principle? So you have the function that is convex, that's my condition inside my domain, and then the function is smaller or equal than 0 on the boundary. That implies that I have also an inequality in the interior. Yeah? If I control on the boundary, I also control in the interior. And how do we prove this one? Here it is important that omega is bounded. Okay? Otherwise it's false. Okay? So there is a relation between 7 and 8, no? Because here in 7 we have the set where u is smaller or equal than 0. And here we are talking about u smaller or equal than 0. So what would happen if there is a point in omega, or there is a non-trivial set in omega where u is larger than 0? Do we get a contradiction?
The line that passes by the point is the contradiction and close to the boundary.
Exactly.
The 7 point, this is convex, we can get a contradiction.
Actually, you're doing better because you're doing actually from the definition. You take a point where u is bigger than 0 and look at a segment that extends to the boundary, yeah? But then you get that on the boundary, the values of u are smaller or equal than 0, Yeah? So in the whole segment, the values of u have to be smaller or equal than 0. That's it. Great. And another nice property is if you take two convex functions and you look at the maximum of these two, you again get a convex function. Why is that true? How can you look at that in terms of the geometry? So when you visualize a convex function, the epigraph is a convex set. No? And when you look at the maximum of two functions, what happens with the graphs? Or what happens with the epigraphs? Let's do a picture. Here's my function u, and here's my function v. What is the maximum? Well, the maximum is now going to be this. So in terms of the epigraph, what has happened? Who said? Is the intersection. And the intersection of two convex sets is a convex set. And also you can generalize this for three functions or even an infinite family of functions. If you have a family of convex functions, then the supremum is also convex. Okay? And I don't need to care if the supremum is well defined or not, because I'm allowed it to be plus infinity. Okay? An example where this happens is the Legendre transform. I define the Legendre transform for an arbitrary function as the supremum of, so the Legendre transform at a point P, which you should think as a slope, is the supremum of Px minus Ux. So for every P, no, I'm sorry, for every x, since of x as a parameter, this is a function of P. What type of function is? It's an affine function, no? As a function of P is affine, no? It's a inner product plus a constant, yeah? So as an affine function is convex. If you define the Legendre transform as the supremum of affine functions, then this has to be convex. There is a geometric meaning, no? So you are looking at the distance between the function Px, let's say this in this picture, and the graph of u, no? And the maximal distance is the amount that you have to translate the linear function in order to touch the graph of u from below. Make sense? In other words, you can also define the Legendre transform such that this linear function is the largest affine function of a slope P below u. Now what happens if we take the Legendre transform of the Legendre transform? So we look at the definition. This means take the supremum now in P of x P minus u star of P. But remember, this was the affine function of a slope P, the largest affine function of a slope P below u. So when you take the supremum over all the possible slopes, no? What you're doing is taking the supremum over all the linear or all the affine functions smaller or equal than u. Yeah? So again, as a supremum of linear function of, or as the Legendre transform of another function, this is always going to be convex. But moreover, we see from this line that this is the largest convex function smaller or equal than u. Meaning that if you take any other function that is convex and is smaller and the graph is below the graph of u, then it also has to be below the graph of gamma. And this is called the convex envelope. In particular, if U is convex, if it's already convex and lower semi-continuous, yeah? Remember what it means to be lower semi-continuous? Lower semi-continuous, well, a geometric way to visualize it is that the epigraph is a closed set. Okay? So you can always touch from below. So if you have that U is convex and low is semi-continuous, if and only if the two applications of the Legendre transform give you back the function U. Okay? So what are some of the relations between these convex functions and Lipsius functions? Well, first of all, convex functions are always going to be continuous, at least in the interior of the domain, and are locally Lipsius. So for example, if you have a function defined on the ball of radius 1 taking values between 0 and 1, then on the ball of radius 1/4, is the Lipsius constant is smaller or equal than 2. And again, this is an application, if you want, of the maximum principle. And look at the picture, no? If you take an arbitrary point x on the ball of radius 1/4, you know the graph here is always between 0 and 1, no? And if I look at this point is on the epigraph, and also this point of this sphere of radius 1/2, no? And a vertical distance 1 from this vertex is also on the epigraph, no? Because the function U is smaller than 1, no? So now if this sphere and this vertex is in the epigraph, and the epigraph is a convex set, also the convex hull generated by this set is on the epigraph. Yeah? So this whole cone is on the epigraph. So that means that for every point you can always put one of these cones from above, meaning that the function is Lipsius. Yeah? Or if you want exercise, formalize this picture into a proof, no? Putting the inequalities as they should be. Another thing that is advantageous about the convex function is, well, you don't necessarily have that the derivative exists. Think about the norm of x, but there is a generalization of the derivatives, and that is the subdifferential. And the subdifferential, geometrically, what they're measuring is the slope of the supporting planes to the graph of U at a given point. So, to be precise, the subdifferential of U at a point x are the set of all the slopes such that the graph of U is above this linear function, no? So x is fixed and c is the variable. Yeah? So for example, here at x1, what I'm saying is that with this slope, this affine function is below U. It may be the case that there are points with more than one subdifferential. For example, here if you have a corner, then you have these two subdifferential, and actually also any other in between those. Okay? There could be also the case, like in this picture, that the subdifferential belongs to two different points. Okay? So for example, here x2 and x3 contain the same subdifferential. Okay? So in other words, P in the subdifferential, if and only if, well, this is what I already said, no? The affine function is below the epigraph of U. So for example, if you take the norm of x, the subdifferential at any point different from the vertex, well, this is just the derivative, no? X over the norm of x. There is no other plane that is going to support the graph at that point. Okay? And a point that is more interesting is the origin. At the origin, you have many supporting planes, no? That you can fit below the graph. Another property, well, what is the relation with the classical notion that we have of differentials? Well, if U is differentiable at a given point, then the subdifferential is just the gradient at that point, and there is also a reciprocus, no? If the subdifferential is just one point, then the function is differentiable at that point, and the differential is just the singleton, no, of this subdifferential. Okay? It's also an exercise. It's not it follows from the definitions. Moreover, this definition is local. Okay? It only matters to see what happens in a neighborhood of the point, not to see the full domain, to compute the differential. So in other words, if you have two convex functions that coincide on a neighborhood of x, then the subdifferentials at the point x are the same. Okay? And the monotonicity, well, let's do this exercise. If you have 2 points, u is convex, and 2 subgradients, p at the point x and q at the point y, then geometrically what this is telling you is that the difference of the gradient and the difference of the point points in the same direction, which is something that we know for convex functions, no? Let me do a picture. So for example, if I look at the function u equals to x squared, yeah? The level sets starting from the origin. Look like this, no? If I take x to be the origin and y any other point, no? So this is the vector x minus y, and the difference of the gradient, so the gradient here is going to point in this direction, and here the gradient is 0, no? So what we see is that these two gradients, well, here is actually better, they are parallel. But usually what we're going to see is that they point in the same direction, no? The inner product is positive. How do we...
Switch P and Q under this.
I made a... Okay. Well, let's do the proof, and then I will see that I got the sign wrong. Okay? So what do we know if P belongs to the subgradient of u of x? What's the definition of that in terms of y?
Uy
Uh-huh.
is greater or equal than ux
Uh-huh.
y minus x.
Great. And then we know that q belongs to gradient of u at y. So what does that mean? Ux so here I have it wrong. Probably does. No, I have it right. X minus y. Now what happens when I add these two inequalities? So these two cancel, I get 0 bigger or equal than p x minus y plus q, y minus x, and q x minus y, which is p minus q y minus x. Yeah? Yeah, I got it wrong there. Sorry. So again, geometrically, so actually they point in opposite directions. So y minus x is this vector, and p minus q has to point in the opposite direction, no? So here p is 0, and q is this one, so p minus q is points in the opposite direction. Okay? So let me move a little bit faster to finish. Stability, well, if you have subgradients, a sequence of functions, and a sequence of points such that the gradients converge to p, the points converge to x, and u converge to u uniformly in a neighborhood of x, then p, this limit, belongs to the subgradient of subdifferential of u at the points x. Okay? You just have to write the definitions and see that everything passed to the limit. Omega open and u convex, then for every compact set inside of omega, this set is compact. So to show that this set is compact, first we have to show that it's closed, but the fact that it's closed follows from the stability, and to show that it's bounded, well, we know that the function u is locally Lipsius. Yeah? So locally Lipsius, when u is C1, no? What it's telling me is that the gradient has to be bounded. Yeah? So the same proof, here you have to check that u convex implies u locally Lipsius is going to imply that if k is bounded, then the subdifferential of u, so this is the union of all the subdifferential for points in k, is also going to be bounded. Okay? The following says that u is open and omega is open and u is convex. Then if u is differentiable at every point, then u is C1. So differentiable means that at every point I can approximate u by its linearization, by a linear function with an error of order o, small o of the distance, no? So the fact that you can compute the differential at every point doesn't mean that this differential of this gradient is going to be a continuous function. However, if u is convex, it's true. Yeah? And again, it's a consequence of the stability, no? So u is differentiable, so that means that the subdifferentiable of every point is going to be a singleton, is going to be the gradient. Yeah? Now, if you want to prove that if u is C1, you want to see that if you have a sequence of points xi that converge to x and a sequence of gradients that converge to p, then p is the gradient of u at the point x. No? Is again the stability. Mollification. So if you mollify with an approximation of the identity, you get also a way to approximate the subgradients by this subgradient. But usually what is going to happen is that this approximation procedure is going to give you more than what you actually need. Think, for example, of the function u, the norm of x, yeah? And see what happens in the ball minus the origin. So the subgradient on this set is just the unit sphere. But when you do the mollifications of these functions, you are always going to introduce all the gradients inside of the unit ball, well, probably minus 0, no? But okay, we can talk more about this later if we need it. But again, keep in mind that this may be an argument that may be helpful to reduce some of the proof to the case where u is smooth. Okay? Subdifferential and level set containing a line. So this is again an exercise if you have a convex function such that on the line that is parallel to En, the function u is equal to 0, yeah? Then the gradient, the subdifferentials are always vectors that are perpendicular to the vector En. Okay? So what you have to think, for example, is you have that the graph is sort of a cylinder, yeah? And you have u equal to 0 on En, yeah? Then all the subdifferentials are always going to point in directions orthogonal to En. So here is the argument. Take an arbitrary subgradient and a number lambda positive. So the definitions tells me that at the point lambda en, so u at lambda en is equal to 0, but this is bigger or equal than u of x plus the product of p, no, with the difference, no? So probably here made a mistake somewhere. P times, yeah, I think I made a mistake. So what we are saying here is u at lambda en is bigger or equal than u of x plus p dot x minus lambda en. Yeah? This is equal to 0, and this is equal to p dot x minus lambda en. Yeah? But now we see is that these quantities, I can consider them to be fixed. And then if I send lambda to plus or minus infinity, I can only get this inequality if Pn is equal to 0. Otherwise, I will get a contradiction. Make sense?
Another way one could see it is if you have any affine function that doesn't have 0 derivative in the xn direction, then for sure it's going to be positive somewhere on the xn axis.
Okay. So let me move on. I think. So let me at least finish with the convex analysis part, and then we can talk more about the PDE part in the next after the break. No. So what's the relation between subdifferentials and the Legendre transform? So first of all, if P is a point, okay, I take P arbitrary, I'm going to look at the definition of the Legendre transform at the point P. Remember, this was the supremum over x of P dot x minus u of x. Yeah? And let me assume that this supremum is attained at a point x star. Yeah? That means that I have this equality, yeah? But then, what this means is that this quantity is bigger than this quantity for every x, yeah? Or in other words, that u of x is bigger or equal than u of x star plus p dot x minus x star for every x. So the graph of u is above this linear function of x. So that means that P is in the yeah, probably I say wrong here. P is in the subdifferential of u at x star. Okay? So I say the other one here. So here you should write P is in the subdifferential of u of x star. And remember that if U is convex and lower semi-continuous, then there is this identity that if you apply the Legendre transform twice, you get the original function, no? So what this means is we have the following lemma. For every x and p, this inequality always holds, no? By the definition of the Legendre transform, no? This is the supremum of this minus that, okay? Moreover, you get the equality if and only if, what we said already, P is in the subdifferential of u at x, yeah? Or, if you see this inequality in terms of u star, x is in the subdifferential of the Legendre transform of u at p. Okay? This is this identity. Instead of using x star, I'm using x. And moreover, if the functions have second derivative, if you take this identity and takes the second derivative, what you get is that the Hessians at x or p are inverse of each other. Okay? This is the chain rule. If you take two derivatives here, one with respect to x, one with respect to p, here you get the identity. Okay. Finally, this is a problem that is going to be in the homework today that Connor is going to send. One of the definitions that we're going to study is Alexander solutions, how to understand these subdifferentials as in terms of pushing measure forward, no? So something that is going to be important to be able to give a precise, a formal definition is to see, well, something that we would like is that the pre-image of these subdifferentials are disjoint, but this is not necessarily the case. However, the set where you can have pathologies, the set where P belongs to the subdifferential of U at two different points, is not that bad. It's a set of measure 0. So this is something that is going to be important in order to define the solutions that we're going to talk about in the afternoon. And finally, an important identity, an important identity to compute these push forward measures, no? So remember that, so here I should have written the determinant, sorry about that. So here, so what does the area formula tells me is that to change variables, no? In an integration, you need to multiply. You need to multiply by the Jacobian of by the determinant of the Jacobian. No, if your way to change coordinates is by means of a gradient, yeah. So what this means is that you're going to take the Jacobian of the gradient, that's the Hessian, and take the determinant. No, so in that sense, no. To compute the integral over E of the determinant of the Hessian of U is equivalent, at least if the function is C2 and let's say convex, no? Is equivalent to compute the measure of the gradient of U, the measure of the image of E by the gradient of U. Okay? And this generalizes for any convex function of class C11. Okay? So what I'm saying here is that this transport, this change of variables is a Lipsius function. Okay? And here I stop. And comments, questions? Sorry about if you felt it was a little bit over the place. And the typos, but I guess we can continue talking during the break and during the recess. And I think Connor will start at 3. Great? Thank you.